Welcome everyone to Electromagnetics ELE531 course at Ryerson University. This is the first time we are offering this course online. This lecture is to review the concept that we have learned in field theory ELE401 in the second year at Ryerson University. This is one of the driest course in electrical engineering. That's why the failing rate in this course is very high, but I will try to make this course interesting for you. Let us start. Electrical engineering is a field of engineering that generally deals with the study, use, and application of electricity, electronics, and electromagnetism. Electrical engineering is based on two theories, the circuit theory and the field theory. You have learned circuit theory in ELE202 and field theory in ELE401. This course is basically the continuation of ELE401, the field theory. In field theory, we have discussed about electrostatic, magnetostatic, and electromagnetics. Basically, the interaction for a static charge is called electrostatic. The interaction for uniformly moving charge or DC current is called the magnetostatic, and the interactions for time-varying charge or current or AC current is called the electromagnetics. So in field theory, we discussed about field electrostatic and magnetostatic, and also we introduced electromagnetics concept. So in this course, we will start from electromagnetics, with the interactions for AC currents. Let us discuss electrostatic first. To understand the concept of a static charge, we need to produce a static charge first. So the static charge can be produced by many ways, like a chemical process or mechanical process. In chemical process, there's a chemical reaction take place to form the ionic bonds. But in mechanical process, we can apply external energy or pressure to separate electrons from the atom. Here is an example for the interaction of static charges. If you rub your dry hair with a balloon, you might see some loss of electrons maybe take place, and one of the object, like your head or the balloon, will charge up with a negative or positive charge, and there will be a force developed between these charged objects, and that will make the hair stand on. So in this figure, you see there is a force between positive and negative charges. The force we can explain with some line of forces. This line of forces is called the flux, and the flux lines actually represents how strong the charge is. As you see, the figure A has fewer flux lines than B, and B has fewer than C. That means C is the strongest, and B is weaker than C but stronger than A. Therefore, the electric parameters that we have learned so far are the electric force and the electric field intensity and electric flux and the density of electric flux. We use some symbols like F for force, E for electric field, D for flux density, and phi for electric flux. So now we are going to find how to relate these parameters, how to find the convenient approach for finding this parameter, and from these above parameters we will learn how to calculate the work done, and we also will learn about the electric potential. Also, we will investigate the properties of electrostatic field, such as the electrostatic field is rotational or irrotational, it is conservative or not, it is divergence or not. So we'll examine this characteristics of electrostatic fields. Let us derive Coulomb's force law. So to derive this Coulomb's force law, we'll start with two charges, Q1 and Q2. The distance between these two charges is r. We need to find the electric force at the point of Q2 because due to the charge Q1. So the electric force will be the product of the charges Q1 and Q2 divided by a constant 4 pi epsilon, where epsilon is the permittivity of the medium times r square. As you know, the force is a vector, so we can write the force F as a vector. So we need to introduce the direction of the force. So the direction of the force is AR. AR is a line joining Q1 and Q2. In order to determine AR, we put this chart system in a reference coordinate system. Like we can choose Cartesian coordinate system and showing x and y axis. So therefore, the distance from the origin to the Q1 is r prime. The distance vector is r prime, and where Q1 is the charge or source charge. So this is Q1 who is responsible for producing the force at point Q2, and this vector is r prime. We use prime to represent the charge related to the source, and Q2 is the observation point, is the location for the observation point. So Q2 is the point of observation where we are wanted to find the electric force because of the charge Q1. And the vector, position vector for from origin to Q2 is R. So therefore AR will be the vector R, the distance vector between A and B, between Q1 and Q2, and over the magnitude of this distance. So you can find the unit vector, and then we replace R with the position vector R and R prime. So finally we substitute these values on the expression, and we'll find the force equal to Q1 times Q2 equal to 4 pi epsilon r, r minus r prime cube, and times r minus r prime. So you can see this is the generalized expression for Coulomb's law. if Q equal to 1, Q1 equal to Q and Q2 equal to 1, then we can write F equal to Q R minus R prime over 4 pi epsilon R minus R prime cube, and this term is called the electric field intensity. For a line of charge with a density rho L coulombs per meter, we can write the electric field expression. So like this. So where line of charge meaning that if the electrons or the protons are arranged on a line to form a charge line, or if the object has a shape, charged object has the shape of a line, then it is called line charge. Similarly, we can write for surface charge and for the volume charge. So this is the relation between force and electric field intensity. So force equal to electric field or times Q. So that's all. So today we have discussed about force, Coulomb's force, and also the electric field intensity. So in the next lecture, we'll cover electric potential as well as the work done and some characteristics of electrostatic field.